Hello there, welcome to my AQA A-level chemistry videos. Hopefully you've used some other videos, and if you haven't, please check them out. If you like them, please let me know how you find them. This video focuses on aromatic chemistry. It's the second lesson of two, so it's lesson 2 of 2. Lesson 1 will focus on the structure and bonding in benzene, and lesson 2 focuses on the reactions of benzene. So as always, we look at the specification when we're looking at teaching, and particularly revision as well, because it helps focus on what we're supposed to be looking at, what we're supposed to know. So this section here is the electrophilic substitution, and you can see it's A-level only. That means it's a year 2 topic, and there's not much to this, okay? There's not much to the benzene topic whatsoever with AQA specification. So ultimately, it's one mechanism, but 2 different reactions. So we look at the nitration and we look at the acylation. Okay, so it's acylation and nitration. It's the same mechanisms in both cases, but we need to look at the 2 different reactions there. Acylation you'll have come across before with acyl chlorides, and this kind of follows on from that. Okay, so first of all then, electrophilic substitution. That's the mechanism. Both mechanisms are electrophilic substitution. Let's make sense of that, okay? Now, from the bonding in benzene, we know that there's an area or a region of high electron density above and below the plane. Okay, so we've got that pi bond, that huge pi bond above and below, where we've got 6 electrons delocalized. That is an area of high electron density, which would result in the benzene being attacked by electrophiles. So an electrophile is something that will accept those electrons. And substitution reactions occur rather than addition reactions, because if it undergoes a substitution, in other words, one of the H's from the ring is substituted by a group, that allows the ring to preserve and maintain the stability of the delocalization. If you were to add to the ring, it would lose electrons from that delocalized pi bond. As you see when you do electrophilic addition reactions in first year with alkenes, we see electrophilic addition reactions with alkenes where the pi bond is actually broken and no longer has that delocalized pi bond. In benzene, substitutions will occur over the addition. Okay, so it is substitution to allow it to preserve that stability. So the mechanism then is described as an electrophilic substitution. And let's have a look at what that might look like. So I'll draw my benzene ring. There we go. And I show the pi bond with that circle there. And an electrophile, I'm just going to notate with an E+. The mechanism, we have the ring of electrons. So this ring of electrons will attack the electrophile. Notice how the arrow is going from the ring and to the E. All too commonly, I'll see students accidentally go the other way around. That's incorrect. So it definitely goes from the ring to the electrophile. We are left with an intermediate then. So the electrophile is now bonded to the ring. It no longer got the positive charge because it's gained electrons from this ring. And the ring now has lost its stability. It's lost that delocalized. It's now a positive charge, and that ring of delocalized electrons has been broken. So what happens now is H, and sometimes people will say to me, well, where's that H come from? What you have to remember is this here is the skeletal formula, and there is in fact a hydrogen at each point here. So there are 6 hydrogens on the ring. It's C6H6. So that hydrogen was always there. We just didn't draw it because we were using skeletal. And what happens is this pair of electrons from this bond now go back into the ring, and that releases H+, and it allows us to re-establish the ring, and we now have our product. So what we've essentially done is we've substituted the E+ and the H+. Okay, that's what we've done. So this is an electrophilic substitution mechanism, and it's the same mechanism for both of them. We will only ever see this mechanism for benzene and nothing else. So this is the only mechanism for benzene. Okay, so benzene will react with different types of electrophiles, and usually we require quite concentrated reagents and a catalyst is needed. Okay, so they're not very reactive, basically, benzenes. They do require catalysts in order for those reactions to take place. And that's because benzene is not very reactive due to the stability. Remember, it's fairly stable. It's more stable than we would expect because of that delocalized ring. And hence we've seen that substitution reactions are heavily favored to maintain that stability. So we're going to look at two electrophilic substitution reactions, and we must study them in detail. So there's two of them. There's the nitration of benzene and there's the acylation of benzene. Those are the only two. And we're only going to look at mono substitution taking place. So we're only going to look at adding one group at a time. Okay. We may well come across, and you will come across even, some benzene rings that have more than one group substituted on, but we will ever only look at substituting one at a time, okay? And that'll make sense when we look at some past exam questions a little bit later on. Okay, so let's look at the first reaction that we need to know about then. So we need to know about nitration and acylation. Let's look at nitration. So nitration of benzene is when one of the hydrogens has been replaced or substituted by an NO2. So in other words, we're going to have a benzene ring and it becomes nitrobenzene, where one of the H's has been replaced by an NO2. And remember, we'll only do one substitution at a time. It would be fair game in the exam for them to then do a second step and have a second nitro. So that's what I meant by only one at a time. So we could see multiple steps, but it will only ever be one at a time. So that's nitration, is replacing a H with an NO2. And the conditions here, so the conditions are we need a mixture of concentrated nitric and concentrated sulfuric acid. So it's concentrated nitric acid, concentrated sulfuric acid, and 50 degrees. Those are essential conditions. Concentrated, 50 degrees. You can't just say nitric acid and sulfuric acid. We have to have concentrated, we have to have 50 degrees. And this is quite often referred to as a nitrating mixture. And I'm going to show you what happens here, because again, this is very common in the exam for you to be asked to show what happens when you mix these two together. So what we do is we add nitric acid with sulfuric acid. Now, sulfuric acid is in fact a stronger acid than nitric acid. So it actually forces the nitric acid to accept the proton, and sulfuric acid will act as an acid. So we end up with HSO4-. So the sulfuric acid has lost a H+. We also make water, and we make NO2+. Okay, and this is the key. This is what we want. This NO2+ is our electrophile. Okay, this is the reactive inorganic product that we get from this reaction, and it's the NO2 that's going to be your electrophile. It's NO2. The positive charge is in fact on the N. Okay, so this is very common to be asked this equation. You do need to know this equation, and like most things in chemistry, don't rely on pure memorizing. Try and make some logic of it. Okay, so we know that we have nitric acid and sulfuric acid. We know that we're going to make the electrophile, which is NO2+. Okay, we also make water, and you can kind of deduce what's left. But we do need to know this equation. Such a common exam question to be asked that, and you'll see that later in our exam. And if you do a class test or any exams and nitration comes up, I can almost guarantee you'll be asked for this equation. Okay. Now, the sulfuric acid actually acts as a catalyst in this reaction, because we saw that the sulfuric acid will make HSO4-, and at the end of the mechanism, the H+ is being kicked out by the benzene, so these two will reform sulfuric acid. So that shows the catalytic properties of sulfuric acid. So the sulfuric acid is used up with the nitric acid to make HSO4-, but it's regenerated. So the sulfuric acid is classed as a catalyst in this reaction. Let's have a look at the mechanism then. So we know that the mixture of nitric acid and sulfuric acid will make NO2 plus, and the positive charge is on the nitrogen. So the mechanism, we have our benzene ring. The electrons will go from the pi bond, from the ring, to the N. The direction of that arrow is very important. That will leave us with a very unstable intermediate because the ring has been broken. We've got a positive charge there now in that ring, and we've got NO2 is now on that ring. We draw our H here. Remember, this being skeletal, we haven't drawn the H's on, so there are H's at each point here. So we've got a H, and then that carbon-hydrogen bond will break. The electrons go back to the ring, releasing H+, and our product, which is nitrobenzene. Notice how I'm drawing the bond to the end, because the nitrogen is bonded to the ring. Okay, so be careful where you're drawing those bonds. And this is the electrophilic substitution. We saw the general mechanism at the start, and it's the same mechanism there. Okay, our electrophile comes from the nitrating mixture of nitric acid and sulfuric acid, and we know that this H+ will regenerate our sulfuric acid catalyst. So our overall equation here, if we were asked for an overall equation, let's do that here. So our overall equation will be benzene, nitric acid is in fact a reactant, and sulfuric acid is in fact a catalyst. So we put the catalyst above the arrow, and this is concentrated, and we have 50 degrees. And that will make our nitrobenzene and water. Water was also a product. So we need to know some uses for nitration of benzene. So what's the point in this reaction? So why do we need nitrobenzene? Well, there are three main uses of nitrobenzene. You don't need to know all these ins and outs and these details. That detail's just there for extra knowledge, really. You don't need that in the exams. You can just remember that nitration of benzene are used in the manufacture of explosives. They're used in the formation of amines, which is the next organic topic we look at. They're also used in other organic synthesis in certain multi-stage processes, because industrial processes will take place in multi-steps, and nitrobenzene is quite often a material in those processes. So those are your three uses of nitrobenzene. So you can literally list them as 3 bullet points: explosives, forming amines, and organic synthesis. So you don't need all the detail, just those 3 uses. Okay, so that's nitration of benzene done. Let's have a look at the acylation of benzene. It follows a very similar pattern to that nitration of benzene. Okay, it's the same mechanism. We need a catalyst. Let's have a look. Okay, so we're going to focus this time. Here, look, on the acylation. We've got a catalyst here. The catalyst for nitration was sulfuric acid. We've seen that. So we're going to look at this Friedel-Crafts catalyst. Okay, focusing right here. So a reminder then, let's try and make links back to previous topics. The acylation of something is adding an acyl group. And your acyl group was your carbon double bonded to oxygen to an R group. That was your acyl group. We saw acylation of ammonia. We've seen acylation of amines. We've seen acylation of water. And we've seen acylation of alcohols. That was in your acyl chloride section. Okay, so acyl chlorides can be used to acylate benzene, but we need a catalyst this time. So when you saw acylation of the amines and alcohols, ammonia, etc., you didn't need a catalyst. You just had that, you just used your nucleophilic addition elimination. This is not nucleophilic addition elimination. We already know the mechanism is going to be electrophilic substitution. So it's slightly different here, okay? We do need a catalyst, and the catalyst is aluminium chloride, and we must make sure that it's anhydrous, which means there's no water there, because if there was water present, we would get hydrolysis taking place. So we must know the condition is anhydrous, and the catalyst is aluminium chloride, which is AlCl3, aluminium chloride. So that catalyst is also known as Friedel-Crafts catalyst. Okay, so when you hear the term Friedel-Crafts catalyst, it just means AlCl3. So why is the catalyst needed here when it wasn't needed in the acylation of water, for example, or the acylation of ammonia or amines? Because benzene is more stable. Okay, benzene requires a very strong electrophile, and acyl chloride isn't in fact a strong enough electrophile, because we need the electrophile to be, if we want an acyl group, we need that electrophile, just like we needed NO2+. So we need this electrophile, and acyl chloride would just be delta plus. It's not a strong enough electrophile. And what happens is Friedel-Crafts catalyst allows us to make this electrophile that we need from our acyl chloride. So this is what happens. If you add AlCl3 to an acyl chloride, so if we add those two together, what happens is the Friedel-Crafts AlCl3 will literally take the chloride. Sometimes we call this a halogen carrier or halide carrier. And that will leave us with our required electrophile. So you can see again, we've got an equation here for the formation of our electrophile. Just as we had in the nitration, we had an equation for the formation of our electrophile there. We have an equation to show Friedel-Crafts producing AlCl4 and our electrophile. Now keep an eye on this, because we know that this is a catalyst. So at some point, this is going to turn back into our Friedel-Crafts catalyst, hopefully. So we're going to show that being regenerated. Let's take a look at the mechanism then. So once we've formed our required electrophile using our Friedel-Crafts, so we've got our required electrophile here, which is our acyl group. The same electrophilic substitution mechanism that we've seen twice so far in this video. The ring of electrons will attack that positive carbon. We get an intermediate that's very unstable because that ring has been broken. We've attached our acyl group, and to re-establish that stability of the ring, the bonding pair of electrons from that CH bond go back into the ring, leaves us with a H plus and our organic product, which is our acyl group attached to the ring. So there's our acyl benzene, and the H plus has been released. So we've got an electrophilic substitution reaction. And we can now show the catalytic activity of the AlCl3, because on the previous slide we saw that AlCl4 was produced because it took the Cl- from our acyl chloride in order to form our reactive electrophile. But what happens now is the H plus that was released in that mechanism will form HCl, and our AlCl3 has been regenerated. So what would our overall equation look like? We'd have benzene, and our reactant would be our acyl chloride, so I'm just going to call it CH3COCl, so I've got ethanoyl chloride there. It will produce our product. There we go. And above the equation, we've got our catalyst, AlCl3, and I'm going to say anhydrous as a condition. And another product will be HCl. So let's have a look at the importance of this reaction then. So why do we do acylation? Well, first of all, it allows us to form carbon-to-carbon bonds. So we're joining two organic molecules together. So that's always useful. Secondly, the carbonyl group that's been added to the ring can then undergo further reactions and make further compounds. So carbonyls are very useful intermediates because from a carbonyl group we can form all sorts of different functional groups. Again, it's very useful in the organic synthesis of molecules. Time for some practice then. So pause the video now and have a go at this question, and when you're ready you can unpause and hear the answer. Right then, so multiple choice. You might see that initially that this equation is slightly different from the one that I told you about earlier because there are different versions of that nitrating mixture. We didn't have 2H2SO4 and we didn't make H3O+, we made H2O. Both are correct, okay, as long as you know one of the two forms, that's fine. So if you're watching this video and you've already learnt this version, then that's fine. Or if you've learnt the version that I've just gone through, then that's fine. Let's have a look then. Quite often in multiple choice, you can eliminate some answers pretty quickly. Well, we know the HNO3 is definitely not a catalyst, okay? The HNO3 is not an electrophile. The electrophile that we make, that's our electrophile there. So I'm eliminating that one as well. Right, so I've got it down to 2. HNO3 is a reducing agent. Well, we could assign oxidation states and have a look through what's happening. Or, if you do recall, that when we put these two together, I said that the sulfuric acid is the stronger acid and acts as an acid, forcing the HNO3 to act as a base, and that's what happens. So in this process, the HNO3 is acting as a base. Next question then. So this is an 8-mark question. Should take in the region of 8 to 10 minutes. So I suggest you pause the video now, work your way through the question, and when you're ready to go through it, unpause. Okay, so we've got methyl benzene reacting with ethanoyl chloride in the presence of aluminium chloride. So this is screaming out Friedel-Crafts catalyst, which is this, and the acylation. And that's what we can see taking place. We're adding an acyl group to the benzene ring. This feels familiar. Okay, so whenever you start a question, always try and think about the topic that it's covering. Obviously, today's video is only going to cover the mechanisms of benzene, but in your paper 2 or paper 1, always get a feel of the question before you start answering it. All too common, people literally stare or go straight to these lines and want to write an answer. Right, so the molecular form. So the molecular formula is the type and number of each atom present in a compound. So this contains carbon. How many carbons does it contain? 1, 2, 3, 4, 5, 6, 7, 8, 9. Contains 9 carbons. It also contains hydrogen. How many hydrogens? 1, 2, 3 there. 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. Anything else? Yes, it contains an oxygen. So my answer here is C9H10O. 2 other isomers are also produced in the reaction. Draw the structure of one of the other isomers. Okay, well, the only thing we can possibly have is instead of having the acyl group here, why don't we have the acyl group here or here? So it's just going to be in a different position on the ring. Be careful, if I put it here or here, they're the same thing, okay? So I'm going to say my structure is, I'm going to draw the structure out, and I'm just going to put my acyl group on a different place on the ring. And that's positional or position isomer. Positional isomerism, 2 marks. Name and outline the mechanism for the reaction of ethanoyl chloride with methyl benzene to produce H. Include an equation for the formation of the reactive intermediate that is formed. Right, okay, well, the type of mechanism, the name of the mechanism is electrophilic substitution. Electrophilic substitution. The equation for the formation of that reactive intermediate, that is showing the formation of our electrophile. So we've got AlCl3 plus our ethanoyl chloride, CH3COCl. That's going to make AlCl4 minus it will also make CH3CO+, and that's our reactive intermediate. Okay, mechanism then. We want to produce H here, so we're starting with methyl benzene. We've got a carbon with a positive charge. That's our reactive intermediate there. Benzene ring attacks the electrophile. Careful with the direction of the arrow. We have a very unstable intermediate where the benzene ring has the stability of that delocalized pi bond has been broken. It's got a positive charge now. I'm making sure I put this in the correct position to suit the question. So I'm putting it in the correct position now. And I also draw this carbon-hydrogen bond in here. That bond then breaks and goes back to the delocalized ring, forming my product. Product has been formed, and we also produce H+. Okay, I could be asked at this point to show the formation or the catalytic behavior of the AlCl3. And if I was asked to do that, I would go one step further and I would say AlCl4- plus H+ goes to AlCl3 plus HCl. Next question. Again, 4 marks this one, 4 minutes. Pause the video. When you're ready, unpause. Acyl chlorides are useful reagents in synthesis. They react with aromatic compounds and with alcohols. We've got an acyl chloride here reacting with benzene, the presence. So this is again acylation. There's our Friedel-Crafts catalyst. Given an equation for the reaction of our acyl chloride with AlCl3 to form our electrophile. So this is a very, very common question. I did say this when I was going through the notes, that being asked for the formation of your electrophiles is very, very common. So we show the AlCl3 becoming AlCl4-, and that then frees up our electrophile. I've made a mistake there. It should be CH2, not CH3. CH3, CH2, CO+, and that's your electrophile. And now the mechanism, what's it with? It's with benzene, so it's again autopilot now. It's electrophilic substitution. This goes towards our electrophile to the carbon. CH2, CH3. I'm going to draw my intermediate now. Does not matter where I put this on the ring. I'm going to put it over here. So carbon, double bond oxygen, CH2, CH3, and I now draw that H on there. That bond breaks, goes back to the ring. That leaves our product. There we go. I'm going to do skeletal and H+. And again, I could show these two coming together to reform AlCl3 and HCl. Haven't been asked for that, but there we go. Next question then. So this question is about nitrobenzene. Again, 5 marks here, should take about 5 minutes. Pause the video, and when you're ready, let's go through it. Nitrobenzene reacts with heat with a mixture of concentrated nitric acid, concentrated sulfuric acid. Yes, I know that, that's my nitrating mixture. And it says it forms, so we've got nitrobenzene reacting to form 3 isomeric dinitrobenzenes. So they're trying to make this question sound harder than it really needs to be, okay? Because they're already starting with the nitrobenzene and they're adding another nitro group on. Write an equation for the reaction with concentrated nitric acid with concentrated sulfuric acid. There we go, to form the reactive species, or the species that reacts with the benzene is NO2+. We also make water and HSO4-. There we go, done. Name and outline the mechanism for this reaction of this species with nitrobenzene to form 1,3-dinitrobenzene. Well, the name of the mechanism, electrophilic substitution. It's the only mechanism for benzenes. Substitution. The mechanism, now here, I've got to be careful. Don't just go into complete autopilot because it wants me to form 1,3-dinitrobenzene from nitrobenzene. So I've got to start with nitrobenzene. I'm then going to form 1,3. What you'll quite often see is when you draw the arrow, I'm going to make the arrow come out at the point where it's going to join the ring. Don't have to do that. So let's draw what we're left with here. It's going to be on this group here is NO2, and the ring has been broken, positive. Draw my H, bond breaks and goes back into the ring. It's going to leave us with NO2, so 1, 3 dinitro benzene, and again H plus has been left. Could show the H plus reacting with this to reform H2SO4 to show the catalyst reforming. Okay, be careful with your arrows. Mine might appear to be quite sloppy, but they definitely start and end at the right places and point in the right direction. It definitely starts, look, definitely starts at the ring, definitely goes to the N. The positive is definitely on the N. Likewise here, there's definitely a positive in the ring. It definitely goes from this bond to the ring, no mistaking. So be careful with the arrows. It might appear that I'm being a bit slapdash, but you've got to make sure that they point to and from and the charges are in the correct place. Right, that brings that video to an end then. Hopefully it was good. Have a little look back over the bonding of benzene if you need to, and look out for future videos. Thank you.